Welcome to the course on An Introduction to Information Theory. I am Adrish Banerjee. So, in this lecture, we are going to talk about block to block length coding. So far we have talked about block to variable length coding, variable to block length coding, and both of these were examples of lossless source compression. Now, to do block to block length coding, we can only get compression because the input block size is also fixed, output block size is also fixed. So, we can only get compression if it is a basically lossy source compression, because our output block size has to be smaller than the input block size, which is, and both of them are fixed. Now, in case of lossy source compression, of course we would like to minimize our probability of error. So, the way we will do this block to block length coding is, we are going to assign code words to those sequences that are more likely to happen. We will assign a unique code word to all those sequences, and the sequences which are less likely to happen, for all those sequences we are going to assign only one code word. So, if we get a typical sequence which is a more likely sequence coming out of that particular source, since we are assigning a unique code word to those sequences at the decoder, we would be able to find out what our message bits were, and we will encounter lossiness or we will encounter distortion when a non-typical sequence, a sequence which is less likely to happen, that is transmitted. So, to talk about block to block length coding, we will first talk about what is a typical sequence expected out of a source. If I say, let us say, a binary source with probability of 0 being 0.5 and probability of 1 being 0.5, what are the sequences which are likely to happen from that particular source if I take a very large block size? We are going to talk about that. That is the concept of typical sequence, and then we will show some properties of these typical sequences which are collectively known as asymptotic equipartition property. We will prove those properties. So, this is the plan for today's lecture. Now, before we go into what is a typical sequence, we need to build up some mathematical preliminaries to prove our results. So, we will talk about those mathematical preliminaries. We will talk about weak law of large number and Chebyshev inequality, and then we will use those results to prove some properties of typical sequence, and these are, as I said, collectively known. These three properties of typical sequence are collectively known as asymptotic equipartition property, and then we will talk about what is the consequence of these properties for block to block length coding. So, we start with weak law of large numbers. So, let x of n be independent random variables sequence with mean mu of x and variance given by sigma x square. So, let x of n be a independent sequence of random sequence with mean mu of x and variance sigma x square. Then the sample mean basically is given by this expression, summation of xk divided by 1 by, and the summation divided by 1 by n. Now, weak law of large number says this converges to this mean mu of x in probability as n tends to infinity. So, let us first show what do we mean by mu of x converges to this true mean mu x when n is very large. What do we mean by this converges to mu of x in probability? So, to prove this, let us talk about, let us say x is a real valued random variable with mean given by mu of x and variance given by sigma x square. Now we denote an event A as follows. So event A is this event that absolute value of x minus mean of this random variable x is greater than equal to some small value epsilon. So we can similarly define the complementary event, which would be the event that absolute value of x minus mean of x is less than epsilon. So we know the variance sigma square is given by expected value of x minus mu x whole square. So this we can write as expected value of x minus mu x whole square given event A has occurred multiplied by probability of event A plus expected value of x minus mu x square given the complementary event of A has happened and multiplied by probability of the complementary event. Now look at these quantities separately. What is probability of this complementary event? This is a probability, so this will be a number between 0 and 1, and this is expected value of x minus mu x square given the complementary event of A. So this is expected value of x minus mu x whole square. So this expected value is also expected to be greater than equal to 0. So then this whole term, this is greater than equal to 0, this is between 0 and 1. So this whole term will be greater than equal to 0. So then we can write that sigma square is greater than equal to this term, because the second term here is non-negative. Okay. Now let's look at what happens when event A occurs. So when event A occurs, what is event A? Event A is this condition. The absolute value of x minus mu x is greater than epsilon. So when event A occurs, x minus mu x whole square should be greater than equal to epsilon square. So we can write then expected value of x minus mu x square given event A has happened is greater than equal to epsilon square. Hence, if I plug this value of expected value of x minus mu x whole square given A, if I plug this value in here, what I get is this expression. Mu x square variance of x is greater than equal to epsilon square into probability of occurrence of this event A, which is this event, that the difference of x minus mu x, the absolute value of that is greater than equal to epsilon. So this event A, as I said, is basically the event that absolute value of x minus mu of x is greater than equal to epsilon. So from here I can write probability of A, which is this, is less than equal to sigma x square by epsilon square, and this relation holds for all positive epsilon. Now let us define this expected value of mu x, mu hat x. This is nothing but, we can show that this is equal to mu of x, which is a mean of x. Similarly, the variance of mu hat, this is equal to sigma x square by n. Okay. So the mean of mu hat x is given by this, and the variance is given by this expression. Now if we invoke this thing, probability of x minus mu of x, the absolute difference, absolute value of that is greater than equal to epsilon, this probability is upper bounded by sigma x square by epsilon square. So in place of x you put mu hat of x, and the mean of mu hat of x is from this expression is given by mu x. So that's my mean of mu hat of x. And what is the variance of mu hat of x? That is this quantity. Remember, I had this probability of x minus mu x. This is greater than equal to epsilon. I had this as upper bounded by variance by n. So here this is my mu hat of x, that's this, and its mean is given by mu x, that follows from here. And what is the variance of mu hat of x? Variance of mu hat of x is given by sigma square x by n. So when I put this variance value here, I get sigma square by n by, sorry, this was epsilon square. Again, just go back and look at this expression. So I'm replacing this by mu x of n, I'm replacing this by variance of mu x of n, and mean of this is given by this expression, and this variance of mu hat of x we just proved, it is sigma square by n. So if you plug these values in this expression, what we get is this. Probability that mu hat of x minus mu x, the absolute difference of that being greater than equal to epsilon, is upper bounded by sigma x square by n epsilon square. Now the same thing I can write in this particular form. So the probability that absolute difference between mu hat of x minus mu x is less than equal to epsilon is then greater than equal to 1 minus sigma x square by n times epsilon square. And here if I let n tends to infinity, then what I would get is probability that the absolute difference between mu hat of x minus mu x is less than some small value epsilon is basically greater than, is almost equal to 1. So that essentially shows that this quantity, when we take limit n tends to infinity, probability that absolute difference between mu hat of x minus mu x, this being less than equal to epsilon, this will basically become 1, because this term will go towards 0, this term will go towards 0, so this probability will be almost equal to 1. So this mu hat of x approaches mu x in probability, converges in probability. So that's what we said earlier, that if you just go back, we said mu, if we define mu hat of x like this, this converges to mu x in probability as n tends to infinity. Now let us define a random variable y. So y is an indicator random variable for this event A. And what is this event A? Recall, this was the event that x minus mu x is greater than equal to epsilon. So what does an indicator random variable do? So it will indicate 1 when event A has occurred, otherwise it will be 0. So we can see that expected value of y is given by probability of occurrence of this event, because y takes two values 0 and 1, right. It takes value 1 with 1 happens when the event A happens, and that happens with probability 1 P of A, and event A doesn't happen, that's probability of this complementary event, which is nothing but 1 minus P of A. So expected value of y is 0 times this probability plus 1 times probability of A. So that's why expected value of y is nothing but probability of A. Similarly, we can define another random variable. We can see that y square will be y. So when y is 0, y square is also 0. When y is 1, y square is also 1. So then, since y square is equal to y, we can write expected value of y square is expected value of y, which is given by this expression. Now, what is the variance of y? This can be written as expected value of y square minus expected value of y whole square. So that will be given by probability of A minus probability of A whole square. So that is nothing but probability of A into 1 minus probability of A, where A is that event, that x minus mu of x is greater than equal to epsilon. Next, we define mu of y as Na by n, where Na is the number of times that event A has occurred out of n times V. So, Na times event A has occurred and n minus Na times event A has not occurred. So, then from the Chebyshev inequality, we can write probability of Na by n minus mean of that, which is basically probability of A. This absolute difference is greater than equal to epsilon, is upper bounded by variance by epsilon square, and variance we have computed. This is basically sigma y square by n. Sigma y square is given by this quantity. So this whole thing is then upper bounded by probability of A multiplied by 1 minus probability of A. So here we have used this Chebyshev inequality form which we have derived earlier. We used this form, right? Instead of mu hat of x, we had mu hat of y, and here variance of y. So we have used this form to get our result, which is this one. Now this result we are going to use later on to prove some properties of typical sequence, and we will define what is a typical sequence. Okay, so just remember this expression, that probability that the difference between Na minus n, Na by n minus probability of this event A, the absolute difference of that being greater than equal to epsilon, probability of that is upper bounded by this quantity. Okay. So now we have developed the expressions that we need to prove some of our results. So now let us talk about what is a typical sequence, and then we will prove some properties of typical sequence, and subsequently we will see what is the consequence of typical sequence for block to block length coding. So as an example, let us consider a sequence of L bits. I am just taking L to be small number 20 because I just want to just illustrate in this particular with a simple example. So let us consider a discrete memoryless source which is emitting a binary sequence zeros and ones with probability given by this. So probability of 0 is 3 by 4 and probability of 1 is 1 by 4. Now my question to you is, which of these three sequences are more likely to have come out from this particular source, this discrete memoryless source which emits 0 with probability 3 by 4 and 1 with probability 1 by 4. So what is this sequence? The first sequence that we see has all ones. The second sequence that we see has zeros and ones, and third sequence that we see is all zeros. Now if we look at probability of occurrence of each of these sequences, because 1 happens with probability 1 by 4, so this will happen with probability 1 by 4 raised to power 20. In the second example we have 1, 2, 3, 4, 5, 6 ones, right, and 14 zeros. So this will be 3 by 4 raised to power 14 into 1 by 4 raised to power 6. So that's this quantity. And similarly the all zero sequence, this would be probability of occurrence. Now the point to be noted is, even though this has higher probability, you can see it's 1 by 4 raised to power 20 into 3 by 20. Even though this has higher probability of these three sequences that we have shown here, this is unlikely to come out of this particular source. Why is this unlikely to come out of this particular source? Because I have been given that probability of occurrence of 0 is 3 by 4 and probability occurrence of 1 is 1 by 4. So if I take large enough block size, it is likely that I should get 0 3/4 of time and I should get 1 1/4 of time. So an all zero sequence or a all one sequence is very unlikely to come out of this particular source. If I would have, let's say, told you this, let's say probability of 0 is 0.99 and probability of 1 is 0.01, then you would have believed if I have said this particular sequence would have come out from this particular source, because in this particular source probability of occurrence of 0 is very, very high, right? But for the source which I have given here, which is this, probability of 0 being 3 by 4 and probability of 1 being 1 by 4, it is unlikely that this particular sequence would have come out from this particular source. Similarly, all one sequence is very unlikely to come out of this source, whereas here if you see, I just mentioned it has 14 zeros and 6 ones, and roughly if you take large enough block size, I expect 3/4 of those bits to be zeros and 1/4 of them to be 1, which is close to what I am getting in sequence number 2. So this is a more likely sequence to come out of this particular discrete memoryless source. So what I will say is, this is a typical sequence which is expected out of this particular source. Now we will formally define what is a typical sequence, and then we will show some properties of typical sequence. So let U be the output sequence of length L which is emitted by a carry discrete memoryless source, and let P U be the output probability distribution of that. So since U is of length L, we are denoting U by U1, U2, U3, U of L. So that's my output sequence of length L. Now each of these UIs, since the source is a carry source, so these UIs could be A1, A2, A3 or AK. Okay. Now let NAI U denotes the number of occurrence of this letter AI in the sequence U, then U is an epsilon typical output sequence of length L for a carry discrete memoryless source if this condition is satisfied. So NAIU by L, this is the fraction of the output. So I have a output of length L, out of them L sequence NAI are the number of basically bits you can say which have AIs. So NAI denotes the number of occurrence of this letter AI. Out of those L input U of length L. So this is a fraction of AI in my output sequence. Now what I am saying is this fraction of AIs in my output sequence of length L, this should be within 1 plus epsilon times P of U AI. It should be within 1 minus epsilon PU AI and 1 plus epsilon PU AI, where epsilon is a very, very small number. You can say if epsilon is 0, essentially what I am saying is this fraction of AIs in my sequence of length L should be equal to probability of occurrence of AI. Okay. So if your L is large enough, then in a typical sequence what you would expect is the number of occurrence of this letter AI, the fraction of the time AI is appearing in this sequence of length L, that should be close to probability of occurrence of AI, and this should hold for all the carry alphabets. So it should hold for A1, A2, A3, AK. So we say U is a typical epsilon typical sequence of length L if this condition is satisfied. Please note epsilon is a small number. So let us illustrate with the help of an example. So we consider the same example that we have considered earlier. So we consider probability of U to be 3 by 4, U being 0 to be 3 by 4, and probability of U being 1 is 1 by 4. Let us take epsilon to be 1 by 3. Then according to this, number of occurrence of 0 should satisfy this relationship. And what is that? So number of occurrence of 0, which I am denoting by N0U, divided by length L, which is 20 here. This should be less than equal to 1 plus epsilon. 1 plus epsilon is 1 plus 3, 1 by 3, that is 4 by 3 times probability of occurrence of 0. What is the probability of occurrence of 0? That is given by 3 by 4. So this is this. And this is lower bounded by 1 minus epsilon. So 1 minus 1 by 3 will be 2 by 3 into probability of occurrence of 0, which is 3 by 4. Okay. Similarly, we can write the relationship for number of occurrence of 1, which I am denoting by N1U. So N1U by 20 should be less than equal to 1 plus epsilon, which is 4 by 3 in this case, into probability of occurrence of U equal to 1, which is 1 by 4. And similarly, the lower bound will be 1 minus epsilon, which is 2 by 3 into 1 by 4. So these are the two, because we had binary source. So number of occurrence of 0 should satisfy this relationship. Number of occurrence of 1 should satisfy this relationship. Now simplifying this, we get this condition that number of zeros in the sequence of length 20 should be between 10 and 20, and number of ones should be between 4 and 6. Now you go back and see the example that we did earlier. Here the number of ones are 20 ones and number of zeros are 0. Here number of ones are 6 and number of zeros are 14, and then in this particular example number of ones are zeros and number of zeros are 20s. Now what did we say? We said number of zeros should be between 10 to 20. So this cannot be a valid sequence coming out of this particular source, because number of zeros are not between 10 to 20. And what condition would we say about number of ones? We said number of ones should be between 4 and 6. So this is also ruled out. So this is the likely sequence. This is a likely sequence which has 6 ones and 14 zeros. This is a likely sequence to have come out of this particular source, which has probability of occurrence of 0 given by 3 by 4, probability of occurrence of 1 given by 1 by 4. Okay. Now let us prove 3 properties of these typical sequences. Now that we have formally defined what a typical sequence is, and we also illustrated with the help of an example what a typical sequence is, now let us try to prove some properties of typical sequence. So we are going to prove 3 properties of typical sequence. The first property that we are going to prove is as follows. So if U is an epsilon output typical sequence of length L, which comes out from a Carey discrete memoryless source which has entropy given by H of U, then probability of occurrence of U is lower bounded by this quantity and upper bounded by this quantity. So let us see how we can prove this. So from the definition of discrete memoryless channel, probability of occurrence of U can be given as probability of occurrence of U1 into probability of occurrence of U2 into probability of occurrence of UL. So that's this quantity. Next, we can also write it in terms of the alphabets emitted by the discrete memoryless source. So since this is a Carey source, it will emit A1, A2, AK. So let's say A1 is emitted NAI times, A2 is NA2U times, similarly AK is NAKU times. So then I can write the same probability in this particular fashion. So it's a product from I going from 1 to K, probability of AI raised to power NAI, where NAI is the number of times this AI is appearing in this output sequence of length L. Now from the definition of typical sequence, we know that NAI should satisfy this lower bound and this upper bound. So NAI will be less than equal to L times this quantity, and it should be greater than L times this quantity. Now let us take the right inequality. So we have shown that probability of U, this is equal to this quantity, correct? Now pay close attention to terms here. This is probability of AI. What is it? It is a number between 0 and 1. Now if you try to raise it to a power which is greater than Ni, so you have a number between 0 and 1. If you raise it to a power which is greater than Nai, then this term will become less, right? For example, half raised to power 3 is more than half raised to power 10. So if I replace this by a larger number, this probability, this term will become less than equal to probability of u. So that's what I'm going to do first. I'm going to replace this NAIU by L times this quantity. So I'm going to use this upper bound first. Now if I do that, so I replace NAI by L times 1 plus epsilon P of AI, and since this term was greater than NAIU, so this whole term, so I am raising a number between 0 and 1 to a larger power, so the equality which was there will be replaced by greater than equal to. Okay. Next, I'll do some simplification. I can write this thing, the same thing in this particular fashion, that 2 raised to power 1 plus epsilon L probability of AI log of probability of AI. So the same thing I can write it in this particular form. Okay, this is not very difficult to show. You can just take this equal to x, take a log of it, and then you can write it. So this same quantity can be written in this particular form. So let's look at the terms here. So I have terms of the form like this: 2 times, let's say A1 into 2 times A2 into 2 times A3, something. I have terms of the form this. Now this can be written as 2 and then summation of these AIs. So that's what I am doing in the next step. This quantity 1 plus epsilon doesn't depend on I, so I can take it out, and the remaining terms that I have is this form. Of course, L also does not depend on choice of I. So what I am left with is something like this. Now this minus of summation from 1 to k of PAI log PAI, that is basically given by the entropy function. So entropy function we know is minus summation of PAI log PAI, right? So then this term becomes 1 plus epsilon L minus of entropy function. So what I have shown you is this: probability of U is lower bounded by 2 raised to power minus 1 plus epsilon L of L times H of U. Now following the same procedure, we can prove that probability of U is less than equal to this. So we'll proceed exactly same fashion. We are going to first write the expression of probability of U, which will be given by this expression. Now instead of taking the upper bound on NIU, we are this time going to take a lower, I am going to take that a lower bound on NAI. So if I am replacing this NAI by a smaller term, then this whole thing would be greater than equal to P of UI. So I would get a upper bound on probability of occurrence of U. So exactly same procedure. Now instead of using this, I am going to use now this. So again I will follow the same procedure. I will replace NAIU by L times 1 minus epsilon PUAI, and since it's smaller than NAI, so this whole thing would be greater than equal to P of UI, and subsequently I will write it in the form of 2 raised to power 1 minus epsilon L times PUAI log PUAI, and following exactly the same procedure we will get the upper bound on P of U. So I just verbally spoke out this proof. The proof is exactly similar to the way we proved the lower bound on probability of U. So following those procedure, we can easily show that probability of u is lower bounded by this and upper bounded by this quantity. Okay. So that's the first property of the typical sequence. So it tells us what's the probability of occurrence of an epsilon typical sequence. The next property that we are going to show for a typical sequence is as follows. The probability 1 minus Pf that a length L output sequence coming out from a Curie discrete memoryless source is an epsilon typical sequence is lower bounded by this quantity 1 minus k divided by L epsilon square P minimum, where P minimum is the smallest positive value of P of u. So let us prove this. So again the consequence of this property would be when n is very large, this quantity will essentially go to 0. Then what we are essentially trying to say is when L is very large, probability of occurrence of a non-typical sequence is very, very small. So we will use this form of Chebyshev inequality that we have proved earlier in this lecture, which says probability of the absolute difference between Na by n by minus P of A. This absolute difference is greater than or equal to epsilon, is upper bounded by probability of A into 1 minus probability of A divided by n epsilon square. So let Bi denotes the event that u takes value such that the condition for epsilon typical sequence is not satisfied. Now go back to condition for epsilon typical sequence. This was the condition for epsilon typical sequence. This was the condition, right? We want number of occurrence of this Ai divided by L. We want this fraction to be within 1 minus epsilon and into P of ui and 1 plus epsilon P of uai. Okay. So clearly when the absolute difference between NAIU by L minus epsilon P of u is greater than some term, then it is not going to be a epsilon typical sequence. So then when Na minus NAIU by L minus P of AI, when the absolute difference is greater than epsilon times P of AI, when this condition happens, we have seen from the definition of typical sequence, when this happens for any of these AIs, then our sequence is not a typical sequence. So what's the probability of occurrence of this? So we can invoke Chebyshev inequality, and the result that we have shown here, we can invoke this result to get an upper bound on this probability. So by doing this, what we get is this expression. Okay. So the probability that u takes a value which is not typical sequence is, this is, now remember Bi is the event that this is not satisfied for Ai. Similarly B2 will be for condition when A2 does not satisfy the condition for typical sequence, and like that for all the K Curie inputs, Curie which are Curie different symbols emitted by the discrete memoryless source. This condition, if this condition holds for any one of these AIs, then it is not a typical sequence, because from the definition of typical sequence we said that this condition that we have mentioned, this should hold for all AIs. This condition should hold for all AIs. So if any of the AIs does not satisfy this condition, then U is not going to be an epsilon typical sequence. So now this probability, when we plug in into this particular expression that we have derived, the probability that we get is as follows. So probability of this event Bi is given by probability of Ai into 1 minus probability of Ai divided by L into epsilon square and P of Ai square. Now after simplifying, we can write this Pu Ai will cancel one of these Pu Ais. So probability of this Bi is upper bounded by this quantity. Now this is a quantity which lies between 0 and 1. So I can further simplify my expression as in this form. So this is a quantity between 0 and 1. This will be this 1 minus this will be less than equal to 1, and if I replace this Pu Ai by the probability of the P min, which is basically probability of U over Ai minimum over all i's. So if I replace it by that, I get an upper bound which is given by this expression. So P in is the minimum non-zero value of P of Ui. Now we define F to be the failure event that U is not a typical sequence. And when will U not be a typical sequence? When any of the event Bi's occur. If A1 does not satisfy the condition for a typical sequence and other AIs satisfy, it's still not a typical sequence. So if any of these AIs do not satisfy the condition for typical sequence, the overall sequence U is not a typical sequence. So if F occurs with in at least one of these events Bi's occur. Now using union bound, I can write this probability of failure as sum of this union of these errors. So this can be using union bound, I can write this as upper bounded by probability of Bi sum over all i's from 1 to k. And we know this probability of Bi, which is given by this expression. So if we plug this value in here, what we get is this expression. So probability of failure is upper bounded by k divided by L epsilon square into P min. So if we plug in this value in this expression, you can see we get the second property of a typical sequence, that 1 minus P of F is greater than equal to 1 minus k times divided by L epsilon square P minimum. So this is the second property of typical sequence. And what does it say? So if L is very large, you can see this probability of PF is a failure. So 1 minus PF, that probability is almost equal to 1. So there is no probability of failure. So if L is very large, most of the sequence that come out of the source are going to be typical sequence. Now let us prove the third property of typical sequence, which is related to how many such typical sequence exist. So the number m of number of typical sequence from a Chiari discrete memoryless source with entropy given by h of u, it satisfies this relationship. Okay. Now to prove this, let's proceed. So we know that Pu sum over all u's, this is given by 1, right? Now using property 1, we have computed lower bound and upper bound of P of u. So if we replace Pu by its lower bound, which is this quantity. If I replace P of u by its lower bound and sum over all typical sequences, then this summation would be less than 1. So, because I am replacing this by a lower bound on the probability of u for typical sequence, and number of sequences will have typical sequence as well as non-typical sequences. So, then I can write that m times this quantity is less than or equal to 1, and from here I get this condition that number of typical sequences is upper bounded by 2 times 1 plus epsilon into L times entropy of u. So, this proves this condition. Now, we are going to prove this. Now, the total probability of epsilon typical sequence is 1 minus Pf, which if I replace P of u by its upper bound on P of u, which is given by this quantity. So, then the total probability of epsilon typical sequence is upper bounded by m times, m is number of typical sequence, into probability of occurrence of typical sequence. This is the upper bound on probability of occurrence of typical sequence. So, then this total probability of typical sequence can be upper bounded by m times upper bound on the probability of occurrence of typical sequence. This we get from property 1. And what is this quantity? We have already derived in property 2. So, we plug in that value. So, from this expression and plugging in the value of P of f, which we defined in property 2, which is this, probability of f is upper bounded by k divided by L epsilon square P minimum, right. So, if we plug this one in here, so we are putting an upper bound on this. So, we are subtracting a larger number, then from here we can get m is greater than or equal to this quantity. So, this is a lower bound on m, and earlier we have computed an upper bound on m. So, combining both of them, we get expression upper bound and lower bound on how many such typical sequence exist. Now, let us try to look at these results when n goes very large. That is asymptotic results when L is very large. Okay. So, we have shown 3 properties of typical sequence and we have proved them. So, now let us look at what happens when L is very large and epsilon is small. When L is very large and epsilon is very small, look at property number 3. What does property number 3 says? Number of typical sequences is basically given by this. If epsilon is small and L is very large, L is much larger than epsilon square, that this term is almost going to 0, and epsilon is a small number. You can see that number of typical sequence are roughly 2 raised power L times h of u. So, from property 1, but for a large L and small epsilon, we can see that total number of typical sequences 2 raised power L of h of u. Now, what does property 1 says? Property 1 gives us the probability of occurrence of these typical sequence. Again, just refresh our memory and see what was property 1. So, if you go back and see what is property 1, our property 1 was this. It talks about probability of occurrence of this typical sequence. Now, if you let epsilon to be very small and L to be very large, you can see this probability of occurrence of typical sequence is roughly 2 raised to power minus L of HU. So from the property 1, the result that we get is as follows. So from property 1 says that each of these typical sequences, so there are total this many epsilon typical sequence, and each of these typical sequence occur with probability 2 raised to power minus L H of U. And finally, from property 2, we get this result that total probabilities of this epsilon sequence is nearly 1. Now go back. What is this total probability? That is 1 minus PF, right? And what is 1 minus PF? 1 minus PF is upper bounded by this quantity. Now again, when epsilon is small and L is much larger than epsilon square, this term will go towards 0. So then this total probability of epsilon sequence is nearly 1. So these three properties collectively are known as asymptotic equipartition property of this discrete memoryless source.